Welcome to the Explainer. Today, we're diving into an electrical system that seems to break every single rule in the book. I mean, think about it. A system that's intentionally designed not to protect itself, but to fight on until it literally tears itself apart. Yeah, we're talking about the incredible and kind of counterintuitive world of fire pumps. This right here, this is the key to everything. This quote comes from the philosophy behind the National Electrical Code. I know what you're thinking. That sounds completely backwards, right? Sacrifice the equipment to save the building? But as we're about to see, there is a profound life-saving logic behind this exact idea. So that's the big question we're tackling today. Why on earth would engineers, whose entire job is usually to prevent failure, turn around and design a system that's built for self-destruction? The answer is pretty fascinating, and it sits right at the intersection of engineering, ethics, and pure survival. So let's get into the nuts and bolts of it. How exactly do you engineer a system that's designed to fail, but in a good way? Well, it all starts with what it's there to do in the first place. When a fire breaks out, the single most critical weapon is water. And that water needs a ton of pressure behind it. And this is the machine that does it. You can think of the fire pump as the heart of the building's entire fire defense. It's this massive motor, and its whole reason for being is to push water with incredible force through the sprinkler system and the fire hoses. It has one job. That's it. Keep that water moving no matter what. Okay, so for this pump to do its one and only job, it needs power. Not just any power. It needs an absolutely bulletproof, never gonna fail source of electricity. And this is where we start to see the first set of really strange rules that make it totally different from anything else in the building. You know, think about the lights in your office, your computer. They're all running off the building's main power. If the power goes out, everything goes dark. Simple as that. But a fire pump? No way. It can't take that risk. So the code demands it has at least two totally independent and reliable sources of power. Redundancy is everything. So how do they pull this off? Well, there are two main paths to power. The first one is pretty clever. It taps into the utility grid before the main shutoff switch for the rest of the building. That means someone could throw the main breaker, kill power to the entire facility, and the fire pump would still be humming along on its own private line. The second path is an on-site standby generator, just sitting there waiting to roar to life if that utility feed ever fails. And the brain behind this whole operation, that's the automatic transfer switch, or ATS. It sits there right in the pump room, and its only job is to watch that main power line. The second it detects a problem, bam, it flips the switch over to that standby generator, usually in just a few seconds. The pump controller never even knows anything happened. All right, so we've got two rock-solid power sources. Great. But what good are they if the cables that actually deliver that power just, burn up in the fire? Because those wires are obviously a huge weak point. And the lengths the electrical code goes to protect these cables are, well, they're extreme and they are not cheap. The best option is to run the wires completely outside the building where the fire can't touch them. If they absolutely have to run inside, they get one of two treatments. Either they're literally encased in 2 solid inches of concrete, or they have to be these special, very expensive cables rated to withstand direct flame for 2 hours. Okay, so we've built this fortress, right? Super reliable power, super tough wiring. Everything is designed for ultimate survival. But now we get to the really wild part. The part that seems to turn all of that logic completely on its head. We're talking about the motor control. Here's the thing. Just about every electric motor on the planet has something called overload protection. It's a safety device. If the motor starts working too hard and drawing too much power, this thing trips and shuts it down to prevent it from burning out. But for a fire pump? Nope. The code flat out forbids it. No overload protection allowed, period. And this quote from an electrical instructor just says it all. It really gets to the brutal core logic of the whole system. The system doesn't care if a bearing is seizing up or if there's a clog in the pipe making the pump work harder. It doesn't want to save the motor. It wants that motor to keep fighting, even if it means destroying itself in the process. So to really grasp how bonkers this is, you gotta understand this one term, locked rotor current. This is the absolute worst case scenario for a motor. It's the catastrophic surge of power it draws when the shaft is completely stuck or locked, but electricity is still being shoved into it. For a normal motor, this would last a fraction of a second before a breaker popped. And here's the rule that just breaks your brain. The circuit breaker isn't there to stop an overload. It is specifically sized to allow that locked rotor current, that self-destruct level of power to flow through the circuit forever without tripping. So let's put some real numbers on this from the example in our source material. For a pretty standard 50 horsepower fire pump, the circuit breaker that's installed is a massive 800 amp breaker. Okay? Remember that number, 800 amps. Now get this. What kind of wire is that 800 amp breaker protecting? It's a number 3 gauge wire, which is only safely rated to handle about 100 amps, maybe a little more depending on the conditions. So wait a minute. An 800 amp breaker on a 100 amp wire? How does that make any sense? What is going on? And that's the jaw-dropping truth of it. The breaker isn't protecting the wire. Not from overload anyway. It will literally sit back and let that wire glow cherry red, melt its own insulation off, and completely destroy itself, just as long as it means the pump keeps pushing water. The breaker's only job is to stop a direct short circuit, which is an even bigger, more immediate threat. The whole system is designed to sacrifice everything for just a few more precious minutes. So why? Why go through all this trouble to create such a brutal, sacrificial system? Well, because when you step back from the circuit diagrams and the codebook, you realize this isn't about wires and motors at all. It's about people. And this is the whole philosophy right here. Run to failure isn't some kind of flaw. It's the entire point. The pump, the controller, the wires, they are all disposable. Because in a fire, the only thing you can't get more of is time. Time for firefighters to do their job, and time for people inside to get out. This system is engineered to buy that time, whatever the cost. So in the end, what looks like a mess of confusing, contradictory rules is actually one of the most focused and humane pieces of engineering you'll ever find. It's a system that says human life is the absolute #1 non-negotiable priority. It's a system designed to win the battle, even if it means sacrificing the soldier. And that kind of leaves you with a final question, doesn't it? This success at all costs mindset is pretty rare, but it's out there. So what other critical systems can you think of where failure just isn't an option and sacrifice is literally baked into the design? Something to think about. Thanks for joining us on The Explainer.